In this class, let us learn about magnetic dipole moment of a current carrying coil. A current carrying coil acts as a dipole. One face of the coil acts as south pole and the other face acts as north pole. If the current flows clockwise, the face has south polarity. The magnetic field at the center of the coil is directed normal to the plane and inwards. And if the current flows anti-clockwise, that face acts as north pole. Here the magnetic field at its center is directed outwards. The magnetic dipole moment of the coil M is equal to NIA, where N is the number of turns of the coil, I is the current through the coil, and A is the area of the plane of the coil. Magnetic moment is a vector quantity. It is directed normal to the plane of the coil from south to north. SI unit of magnetic moment is ampere meter square. If a current carrying coil is kept in a magnetic field, a torque acts on the coil. The torque acting on a current carrying coil in a uniform magnetic field is given by mb sin theta, where m is the magnetic dipole moment of the coil. Therefore, m is equal to torque by b sin theta. From this equation, the unit of m is joule per Tesla. So magnetic moment can be defined as the maximum torque acting on a current carrying coil in a uniform field of 1 Tesla. Now let us see the magnetic moment of a revolving electron. In the case of an atom, the electron revolves around the nucleus. The electron performs uniform circular motion around a heavy nucleus, and this constitutes a current. As the electron moves clockwise, the equivalent current will be in the anti-clockwise direction. The equivalent current I is equal to charge flowing per second Q by T. That is equal to E by T, where T is the time period of revolution. It is given by circumference of the orbit, that is 2 pi r, by velocity. Therefore, the equivalent current I is equal to EV by 2 pi r. So, the magnetic moment associated with the circulating current can be calculated as M is equal to NIA. If we are considering single electron, N is equal to 1. I is equal to EV by 2 pi r, and A is the area of the plane of the orbit, that is pi r square. So, magnetic moment is equal to EVR by 2. And the magnetic moment is directed outwards because the current flows anti-clockwise. So the current loop has north polarity. So the magnetic moment is directed from south to north or outwards. But the angular momentum of the electron R cross P, the angular momentum, is directed normal to the plane and inwards. So magnetic moment is directed opposite to the angular momentum. Let us write this equation in terms of angular momentum. Let us multiply and divide by m, and mvr is the angular momentum of the revolving electron. So m is equal to E by 2m into mvr. MBR is L. So we can write magnetic moment is equal to EL by 2m. Since magnetic moment is directed opposite to angular momentum, in vector form we can write it as M is equal to minus EL by 2m. It is the orbital magnetic moment of the electron. The ratio of magnetic moment to angular momentum is E by 2m. It is known as gyromagnetic ratio. It is equal to 8.8 into 10 raised to 10 coulomb per kilogram. According to Bohr atom model, angular momentum is an integral multiple of h by 2 pi. L is equal to nh by 2 pi, where n is equal to 1, 2, 3, etc. Principal quantum number. Therefore, the magnetic moment is E by 2m into nh by 2 pi. If n equals 1, or the minimum possible value of m is given by EH by 4 pi m, it is known as Bohr magneton, and its value is 9.27 into 10 raised to minus 24 ampere meter square. Any charge in uniform circular motion would have an associated magnetic moment, and this magnetic moment is known as orbital magnetic moment. Thank you.